started our study of interacting quantum field theories, and we said that we're going to consider theories where we can think of a free piece of the Lagrangian density and an interacting piece, which therefore means that our Hamiltonian would also have a free piece and an interacting piece. We have to make some working assumptions to get somewhere. And the simplest one is that there exists a state, there exists a Hilbert space, there exists a state in the Hilbert space called the ground state. We will assume that it's unique. We're going to call it omega. Of course, it's normalized. And when the full Hamiltonian acts on it, we get some eigenvalue that we call the vacuum energy, called E0. And I also told you that the goal of the whole week, after working so hard for the past 4 days, and today too, is going to be the computation of this, okay? But what do I mean by the computation of this? Well, I mean translating this object into something that we know how to compute, something that is made out of objects we know how to deal with, okay? Since this was the goal of the week, it therefore, and today is Friday, it becomes the goal of today. Okay. So we said there are several pieces we have to understand. One piece are the operators, and the other piece is the vacuum. If we understand how to express this in terms of things that we understand, that we know how to handle, then we can hope to calculate this object. So we said that yesterday we said that at a fixed time, t0, we can model the field as if it was a free field at t equals to 0, okay? So we have this object, and we said, well, that doesn't seem to be very useful because if we want the field at any other time, we have to evolve this with the full Hamiltonian of the theory. Now, our theory is relativistic, okay? So we're assuming that our theory is Poincaré invariant, okay? And given that it's Poincaré invariant, there is a conserved charge associated with translations in time, and that's going to be our Hamiltonian. That's why we can freely say that we're going to evolve our states using the full Hamiltonian of the theory. So we have that this would be the value of our field anywhere at any other time different from t0. But this seems a little bit too hard to calculate. So we're going to introduce an auxiliary object. So yesterday, after the lecture, there was a lot of discussion about what evolves in time and what not. So let's settle from now that evolution in time we're going to take as a physical evolution, meaning something that is generated by the physical Hamiltonian, the full Hamiltonian. Any other thing that we can produce that depends on time, using any other operator will just be that, will be an operator that depends on time, okay? Let's try to avoid using terminology like saying, well, we're going to evolve this using some other operator. No, there is only one evolution in time, and that is with the physical Hamiltonian, okay? Of course, I'm not going to follow the rule, and I'm going to keep saying, well, we are going to evolve this with, but I'm warning you. You shouldn't pay attention to that part of the speech. It's just hardwired, and it's going to be hard not to say it. So we're going to define an auxiliary object by doing what? Well, by taking phi of t0, x, and pretending that it's actually a field in a free theory, so we can evolve it with a free Hamiltonian, right? So that was meant to be a joke, okay? That was a good one. So this is an object. Who cares what, who cares how we call it, okay? We're just taking this guy and applying these operators to it, okay? So we shouldn't call it anything. But well, it's too long to write it. So we're going to call it something. Okay. This I, as I said yesterday, is traditionally called the interaction picture, this and that, but let's forget about names. Let's just say that this object, that's the name we're going to give, and it's defined like this. Okay. Now, this object, we know exactly what it is, of course. All we have to do is to take the original formula and replace t in the formula by t0 by t. So we know exactly what this object is. So this is a good object. So we know it for all times. Now, we want to express the object we don't know in terms of that object. So the physical field at a time t is going to be, so if we want to get it, what do we have to do? We have to do this t minus t0. We have the field phi at t0. And we have e to the minus I h t minus t0. We want to somehow put phi I in here. So the trick we used yesterday was to put the identity in the form of e to the I h0 t minus t0 minus I h0 t minus t0. This is the identity operator, and here too. Okay. Now this object is what we call phi I, which we know, so that's a good thing. This we don't know, but we're going to give a name to it because it's also very long. Traditionally, it's better to call this one, to give a name to this one first. Okay. So this one is called u t t0. Clearly, this operator here is the dagger of this operator. Do you all agree? Good. Now, having named that one, this one is just u dagger. Now, is u unitary? I somehow gave myself away by the name, but what do you think? Yes, it is, right? Because if we just dot these two operators, this one cancels this, giving you the identity, and then this one with this one gives you the identity. So step one is to compute this operator. This operator has a name. It's called the time evolution operator. Yeah, we shouldn't, but it's, I know. And we have to learn the terminology. It's like, that's how what people call it. Of course, we're not going to call it like that. We're going to say you. So we have to compute it. So the first observation is trivial, right? That if we have this as a function of t, at t equals to 0, t equals to t0, is just the identity. Okay? Now, if we could only find a first order differential equation that this object satisfies, then we will be in business because we know an initial condition for the object. So that's the goal, to find a first order differential equation for this operator as a function of t. And then, well, if you want to do that, the first thing that you should try is take a derivative with respect to t of the object and hope that you can write down whatever is here in terms of things that you know. Okay? So let's do it. So we have our operator here. When we take a derivative with respect to time, so what do we get? So we're going to apply a derivative with respect to time there. And I think here this is supposed to be an I, right? No, a t. So let's take a derivative with respect to time. The derivative acts on this operator, and it gives us I h0 e to the I. Well, it gives us back the same operator again, right? Sorry? Thank you very much. So when we multiply by the I, we get a -1. So now we apply it to the next operator, and we get e to the I h0 t minus t0, and then we get the I that we had here times minus I h e to the minus I h t minus t0. Okay, so this whole thing gives us another plus sign.
How do we know which way to drop the terms off? Because these are operators. Like h is an operator, right? So
Yes, I didn't do it at random. Did you realize that?
Yeah.
So, of course, here I can put it. Can I put the h here? Why? Because it commutes with this. Can I put it here? No, I didn't. Exactly. So that's, yeah, very good. So we have to be careful, and I think I was. So let me just check the convention that the operator is I and not minus I. No, it's I. So that's fine. Yes. Okay, so that's the operator that we want to compute. So what do we learn? We learned that this is equal to what? Sorry? Yeah, it looks very strange, right? So let me do something. I really want to write the whole thing in terms of u again, right? So what do I have to do if I want to write it in terms of u? I have to translate this in terms of u. So let's see, what do I do? So I have h. So in order to make up a u, I have to multiply by this, actually by this whole thing, right? So you get h e to the minus t0, sorry, t h0 t minus t0. And then I produce my u t t0. Do you agree? Do you see what I did? Yes. So that's how I fix this term. Do you all agree? Okay, very good. Now I have the h, and I have this guy here. Okay. Now I have my u, and I have something that looks like this now. Okay. It's very, very tempting to just say, well, this guy can go inside and put it inside here. But in fact, that's something we can do because h0 commutes with hc, with this operator. So we can actually write this as minus e to the I h0 t minus t0, h0 e to the minus I h0 t minus t0. Right? Nothing deep there. So this is e to the I h0 t minus t0. Now I have h minus h0 e to the minus I h0 t minus t0 on mu t t0. That looks pretty good. But this, by definition, is our interacting part. Okay? And this object is the definition of the object with a label I. Okay? I refuse to say interaction. So, so this object here is defined as hi of t. Okay? Definitely, it's an object that depends on t because we're applying these operators, which are not evolution operators, right? Because the only true evolution operator is a one with the full Hamiltonian. This is just a trick, okay, to produce something that depends on t. And therefore, we find that our u operator satisfies this differential equation. So it's a first-order differential equation with a boundary condition. So that looks pretty good.
Sorry, technically there should be an int and an I on it, right?
This is my definition of what this guy is. Yes. Yeah, in principle, yeah, it's true. I should put an int somewhere, but that would be yeah, I'm defining. Once again, this is some auxiliary operator, and I'm calling it hi of t. Right. Now, how many of you are familiar with first-order differential equations of matrices that depend on t, where the entries depend on t? Have you ever seen that before? Right, so this is exactly the same, except that these matrices are infinite dimensional. But, but the technique to solve it is exactly the same. So if you saw that in your differential equations course, which I'm sure many of you have, the technique we're going to use is exactly the same. So there is nothing fancy about it. It's just that it's an infinite dimensional matrix. So the solution well, since I took that course, I know what the answer looks like. So, and also it's in the book. So I'm just going to write down what the answer is, and then we're going to check that it's true. Okay. So once again, we're going to go from the direction that only requires skills and not inspiration. So the solution, or this is a claim. The claim is that the following is a solution. So once again, those of you who have seen differential equations for matrices would recognize this. Do I have to write one more order, or you think this is okay? So can you figure out what the next? This is an infinite series. Okay. So this is an infinite series. The next term contains 3 integrals. Again, they are going to go. The next one will go from, say, t0 to t2, okay? And it's going to be an integral over dt3. And the Hamiltonians, these operators will be written in this order. And now you're going to see why, okay? Because we're going to check that this is a solution, and it's a solution if they are written like this. Yes?
Sorry, should that first T0 be T1 in the second term?
No, it's T1.
Is that okay? Yes.
So you talked about the particular order in which HI is written in this way.
Yes.
T1 first and T2. So you're saying that my Hamiltonian interaction picture should not, a priori doesn't commute with itself at different times.
No, it doesn't commute. There is no reason why it should commute. Okay? So now, let's check that this is indeed a solution. So we are going to apply the differential operator on my ansatz. The first term is trivially 0. Then I have I times minus I, the differential operator acting on this. But the only time dependence is here. The only t dependence is here. And therefore, the derivative, all it does is to evaluate the argument at the value t. The next term is I minus I squared. Same thing happens. So I'm evaluating the argument or the integrand at the value t. So I remove this integration, and I evaluate everything that has a t1 at t. So t1 becomes t. Actually, I could have written it here because this is an integral over t2. So it goes out. And the integral becomes an integral from t0 to t because t1 is becoming t. And now I can relabel t2 if I want, right? T2 is a dummy index. So I can relabel it and call it T1. So this used to be T2. And again, I have I, T1. Now you can see that the pattern continues, right? That's why we need an infinite series. We cannot stop at any point, otherwise we won't get a solution. So this thing here gives me, what does it give me? It gives me +1. This thing gives me, what do we get? Minus I, which is good, right? That's what we need. So we get exactly hi times our series back. Okay? So that's pretty good. So we were able to solve the equation as an infinite series, but well, not bad. Yes?
Does the fact that it works somehow imply that the series also converges if you write it that way?
Let's not get into things that converge or don't converge.
But
Almost nothing converges here. Yes, but that's a secret for us.
So just because it's solved, it doesn't mean that it was converged.
It's a formal solution, say. Yeah, it's a formal solution, and we will deal with it. Okay. Now, once again, this takes a long time to write. So we're going to introduce, maybe I should do it. We're going to introduce a nice little trick. And the trick is the following. Let's take the second term. We said the second term is an integral from t0 to t1, sorry, to t, dt1, integral t0 to t2, dt2, hi t1, hi t2. Okay? So what I'm going to do is to write this as half the integral from 0 to t, t0 to t, dt1, integral from t0 to t again, dt2. But now, you see that when I do this, sometimes the Hamiltonians will be in the wrong order. So the claim is that if I put a time ordering operator, I can fix the problem. So is that true? Well, in order to see that it's true, the standard way that you will find everywhere is that you draw T1 and T2. Sorry, you draw T1 and T2. Then you have T0, the particular value of T1, some particular value of T1, T0. So this was the original integration that we had. And then all we're doing is doubling the integration, but then putting these guys in the correct order, okay? So the operator will manage to convert the integrals into two pieces of this integral, one over each triangle. Sorry, these integrals go up to t. Okay, those are my integrals there. Is this clear? Well, your exercise is to show that the same happens for the next term. Moreover, your exercise is to show that the next time you actually get 6 copies of the same object. Sorry, this is supposed to be T1, right? Somebody's not paying attention. That's, well, in particular. So this was T1, and now T2. The next one is T0, T2, dt3, H1, T1, HI, T2, and HI, T3. So the claim now is that if you draw this in 3 dimensions, it will overshoot by precisely a factor of 1/3 factorial. And you can go from T0 to T, dt1, T0 to T, dt2, T0 to T, dt3, and the time ordering of H, 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 the 3H that we have here. Clearly, there are 6 possible time orderings, right? So each one of them will give you a contribution from one of the regions, and they will all be equal because the time ordering will fix it, and you would cancel it with a factor of 3 factorial. Very good. So having done that, we can now write down what this looks like in general. Actually, we can write down the nth term very easily, and we will here. So we can now say that UT-T0 is equal to a sum from n equals to 0 to infinity of what? So we have all these terms. Well, it's kind of, well, yeah, we need minus I to the n over n factorial T0 to T dt1 Tn T0 to T, and the time ordering of these operators. Okay. Now there is something interesting, which is that the time ordering is something that is fixing our operators. So inside the time ordering, we can do anything with our operators. We can commute them freely, right? Because after all, the time ordering does something to them. So it fixes them to be in a particular order. So whatever we start with is completely irrelevant, okay? So what we're going to do is to put the time ordering outside of the sum and pretend that these objects completely commute with each other, right? As I said, we can pretend that they have any order we want because the time ordering will come and fix it at the end, okay? So we're going to put the time ordering outside, and if we do, each of these integrals become a single integral, becomes an independent integral, and we have the nth power of that integral, and therefore we get this sum becomes nothing but an exponential of what? Well, it becomes an exponential of minus I, the integral from T0 to T, dt prime of hi t prime. Okay? And that's our master formula, which is called Dyson's formula. All right. Okay. Yes.
Is it, I don't know, maybe obviously it's not that as rigorous, but could you have just done this by sort of like a solution by recognition when you just see that differentiating with respect to time, you just get hi of t down. So by recognition, you see that u of t will be an operator which has an exponential.
Well, if u was a regular function and h was a regular function, indeed the solution would be this without the time ordering, right? So we cannot use that intuition, right? Because this object without the t is extremely different from the object with the t. Okay.
So
when we put the integral inside the time ordering, because the time ordering operator only acts on the Hamiltonians, not the measure. Can we think of that coming to the last expression from that point of view?
Yeah, all I'm saying is actually something. All I'm saying is that once you take this object, let's go backwards actually. You take this object, you expand it, right? Once you expand it, then you will worry. Oh, when I'm expanding this, I have to worry because these operators don't commute. So what do I do? So what I'm saying is that forget about. Don't worry so much. Just expand it in whatever way you want. Because this guy, no matter what you did when you expanded it, it will fix it. It will give you a unique answer. Okay? Indeed, you can pass it through this because this is an operator that only acts on operators. Okay? I mean, that was our definition of the time ordering. It's basically a definition, if you want. Yes.
So T, we should have to really represent T as say a matrix or something. It acts only on operators. You cannot define its action on a basis.
Well, we defined T last time as just a simple-minded operation of taking carefully the operator, saying, well, when these guys are here, 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 I multiply by theta functions, by step functions. That's literally what I mean. Nothing fancy. Okay. So let's study some properties. So some properties of this operator, and some of which don't follow very easily from the definition we had, but they follow very easily from the formula in terms of the time ordering. Okay? So the first is called the group property. And what is that? Well, suppose that we have, so let's check. T is greater or equal than T prime, greater or equal than T0. Okay? Now, what is the following? Say you have U of T. Now, you see, there is something interesting. Now, this is an operator. T0 was just a reference point. So we can actually define this thing for any value of this. We can just put any number here. T0 was just a parameter. Okay? So we can treat this as a function of that parameter. So we can define this object and ask, what happens when I have a composition like this? These two operators, one acting after the other. What do you think we get? Yeah, that's what we would like to get, U of T, T0. So that's the question. Is this U of T, T0? Well, you see from the definition we had of the operator in terms of the full Hamiltonian and then the operator H0, that it's very hard to derive. But now, once again, you say, well, this guy is the time ordering exponential of minus I T prime to T, okay, Hi of T prime. Oh, we cannot call it T prime, right? So it should be double prime. Very good. The most difficult technical problem of the lecture has been solved now. It was what to do with the notation. Okay, that's this guy, and now we have time ordering exponential of minus I integral from T0 to T prime Hi of T double prime dt double prime. But now there is something fascinating, right? All these operators are naturally evaluated at times that are smaller than all the operators on this side. Right? Because that was my assumption. So that means that I can really put them all inside a single time ordering operator and treat everything inside as if they were commuting operators. No problem. So this thing becomes t of the exponential of the integral. Now, when they combine this integral with this integral, nicely merges as an integral from t0 to t of h t double prime t double prime, which is nothing but this operator. So this is great. Okay. So the next property, yes.
We're considering time to be positive, right?
The time. Well, it doesn't matter, right?
But I mean, here this, you call it a group property. You will have evolution operator to do another evolution operator, right?
Yes.
You cannot define an inverse for this, right?
You bet.
It should be a semi-group, right? You want, I mean, yeah, that is the inverse, but you that is not in the group, right? Because it requires group minus.
Okay. So let's see. What is U dagger? Now that you mention it. So, well, first of all, the dagger acts on the I to give us a plus I, integral from t0 to t dt prime. But of course, this object is Hermitian, so we do nothing to it.
What about T dagger?
Which T dagger?
Time ordering? Is no dagger.
The time ordering was a very low key object. Remember, it just a bunch of step functions. So the step functions don't do anything, right? They are just 0 or 1. Yes.
For example, for the time ordering of two product of operators, one into the dagger, swap to the
Exactly, that's very important. But the time operator tells you that these guys commute, basically.
But this says, but the time ordering says h t0 before or t1 or after t1, and because of the dagger, and the dagger changes that to t1 before to the other way around.
Yeah, the other way around.
Yes, so it's a start. Yes, they got it.
That's still correct. They got it.
Yeah, but you have an integral here. Redefine your variables such that one goes before the other.
You have the first is already under time order operators. What? It's already under time order operator.
I don't. The time ordering has become reverse time.
Okay, that's a good idea. So you're saying the time ordering has become a reverse time ordering. Okay. Okay, so let's see what happens. So you have the exponential minus I. Now it's integral from t to t0 dt prime hi t prime, right? I just flip the contour and put a minus I here, right? Now, but I mean the high school change of. Okay. Well, but this is precisely what we should define as a time ordering operator that takes, I mean, as an evolution operator from t0 to t, right? Precisely with a time ordering operator that takes into account the path. So this is more generally thought of as a path order exponential. Very good. Yeah, everything ended up working. Okay, so this is our inverse. All right.
So in the context, for example,
It's not a joke. You can see I have the T-bar.
in the context, for example, of quantum open systems, you have exactly this same expansion, right? And in there you have your evolution operators don't have an inverse in terms of this, so that your evolution is not reversible, right? So in this case, we're saying that I have a reversible evolution. I mean that my interactions are...
Well, as Tibra would like to say, this is a closed system, right? We're considering the whole, this is a system that is defined in the whole space-time, right? I mean, there is no, there is no room for saying that you are interacting with an environment. This is a theory of something that lives in the whole space-time. Yes?
Can you explain again the difference between T and T-bar?
Yes. T-bar is a path order operator. So what is a path here? Well, you take, in the space of times, you just draw your path, right? Any path, actually. You can even complexify time if you wanted. Then you go from T to T0, okay? Or whatever happens to be here. And then the definition of the T-bar operator is something that orders things according to the order in the path, okay? So you will find that in gauge theories, in the next, they will, right? They won't see Wilson loops. So you will not find this. But sometime in the future in your lives, you will find something that is called a path order exponential, and people usually denote it as P. And the P has the meaning of path.
Let me reformulate a little bit my question, because I have this T.
Yeah, let's discuss that after the lecture if you want. I mean, being in a defining a statistical mechanical system is out of the scope of this course, right? So let's discuss open system or systems that interact with something else after the lecture. Okay, let's try to concentrate on what we want. I mean, what we are trying to do is already complicated enough. Okay. Yes.
So, would it be incorrect to write T-bar on that line, on that board? Like, is T-bar...
No, we can put a P everywhere. Okay. We could have started with a P everywhere. Yes. This looks good, right? So we should keep this. This is our goal of today. Okay. So what's next? I use these ones for. No, we might keep this. Well, we remember this. And that guy went over there. Okay. Okay. So from which formula? Where is it? So we don't have it anymore. But now we know we have under control our operators, right? Maybe we can put it here and keep it. So we now have under control our operators, because we say our operators at any time can be written as U dagger T T0 on these operators, which we know what they are, U T T0, and we have found what U is. Okay, so this is check mark. Out of the two things we had to find, we have found one. So we need to find the other one. That's what we're going to do. So the vacuum. And now you're going to see why we made all the assumptions we made last time, because I want to be able to do the calculation we're about to do. But the assumptions were not unreasonable. Remember the assumptions, one of the assumptions was that the vacuum of a free theory is a vector in the whole Hilbert space of the interacting theory. And the other assumption we had was that the overlap between the free theory vacuum and the vacuum of the interacting theory was different from 0. Well, the next thing, which is not an assumption, is just based on the fact that the Hilbert space exists, is that we have a completeness relation in the whole Hilbert space given by the eigenvectors of our true Hamiltonian. Okay, so let me define a set of eigenvectors of the true Hamiltonian to be denoted as vectors with an index n. Okay, this index n could be continuous. In fact, we're going to see next week that it's continuous. It has discrete values, but it could be continuous after some point. But let's not worry about that. Let's simply say that the true Hamiltonian has some bases, and it can be diagonalized in that basis, and these are the guys. Okay? Of course, the vacuum belongs to that. So the vacuum is the 0th guy, as we said somewhere over there. Okay? So we have a completeness relation. We're going to isolate the vacuum because, well, that one is, it's going to be important. That's the thing we want to get. It's both.
But it excludes 0, right?
That's right. So the vacuum is here. So I extracted the vacuum. Okay. But this guy is in our Hilbert space, right? So we can apply this operator to the vacuum of the free theory. And what do we get? So let's apply this operator to this. Let's say 1, 2, and 3. So combine 1 and 3. And what do you get? You get, well, you get this guy back here has to be equal to this plus our fancy sum or integral. Okay? Well, then we're almost done, right? This is what we want. So we can get it from here. Okay. So our goal is to find this vacuum. So the vacuum is expressed as this over the vacuum minus the rest, which we're not even sure what it is. Could be a sum or an integral or both. In fact, I think it's both. We have this. So this is just a trivial identity, right?
Assuming that the spectrum is not degenerate?
The spectrum of what?
Of the Hamiltonian? Or you include that even there?
All that. The only thing that I'm assuming is unique is a vacuum. Right. Okay, so this is a very clean formula, but it's also a very useless one. Right? Just like this, it's not telling us anything. It's telling us what the vacuum is in terms of things that we don't know. So we need a trick to isolate, just to express this in terms of things that we know, okay? Or at least get closer to it. And the trick is the following. We're going to apply the true Hamiltonian. Now we're going to evolve this in time. Now we're allowed to say it. Yes?
Could you say again why we're trying to find the vector?
Oh, because we want to compute. I mean, for no reason whatsoever, we want to compute this. I haven't told you why, but trust me, it's going to be important. So we want to compute it. We found this, and now we want to compute this somehow. Okay. So in fact, the trick is a little fancier than this. The operator that I want to apply is minus that. It's actually fancier. It's plus T0 H. Right? So that's what I want to do. Okay? Well, T0 is obvious why, because T0 was this reference point that appeared everywhere. So it's even in the definition of our operators, phi. So it's a natural thing to do, to put it here. So we apply this here. We apply that here. Capital T is a number. Sorry? Oh, yes. It's not a time order. Yes. Yeah, we should use something else. Let's call it. But T is going to be a very large time. So how do you want to call a very large time? I'm afraid that capital T is the only natural. Capital tau. Oh boy, yes, okay. It's a calligraphic T, capital T.
Is that the actual symbol for the time?
Oh, please. Okay.
That is the one on Wikipedia.
Okay, whatever it is, this thing is obviously this, right? And now if you apply the same thing to the other side, we're going to get this operator, which we don't know how it acts on this guy. But we know what it does to the rest. So we get e to the minus I t plus t0 en n. Okay. Very good. So what do? Let's divide by this, because after all, that's what we want. We want to get the vacuum from this formula. Skip this there, and let's do it here. Okay, so our vacuum is now e to the minus I, this t plus t0, h acting on the vacuum divided by e to the minus I, t plus t0, E0 minus the rest. Now I'm not going to bother to write everything else. I'm just going to write e to the minus I, t plus t0, en minus E0 times the rest. Okay? You all agree that that's what it is, right? Very good. Now here comes the trick, really. This is true for any value of this capital T, but we can choose one value of capital T so that the only thing that survives in the limit, or that the only thing that dominates, is this quantity. Now, by assumption, this is always greater than 0. The vacuum is unique. Now you see why I need the vacuum to be unique, right? We need all those states to be, that difference to be always positive. So if we choose this to be some very large, so if that's positive, say that I choose this to be some quantity, I mean, it goes to infinity with an imaginary part. So this imaginary part is minus I. With this minus I, we're going to get a minus. And in the limit, we're going to find that all these terms drop out. Okay? Of course, in this case, there is this term here, but this is not, these guys are actually subleading compared to that. Okay? So this is a way to project out all the other states. This is something that, this is a trick that is done very often. Okay? So we conclude that our vacuum is the limit when we take this quantity capital, calligraphic capital T to infinity, but along this particular direction, okay, of this object. Well, it looks like something very complicated and that we still don't know what to do with it. But let's actually do something interesting here. You see, we have the vacuum. So we might want to recover something that we know how to deal with. So this operator has the full Hamiltonian in it, right? What's the only thing we know how to deal with that has the full Hamiltonian in it? Well, the U operator, okay? Well, it's not the first time we have converted something like this into something that has a U operator, right? So let's actually do it. Yeah, so put this guy was really in the numerator, right? So what do we get? This object will now go in the numerator, and then, let's see. Did I put that correctly? I think. Sorry?
H acting on the zero state gives you an E0 contribution, which is 0 times infinity, which doesn't.
Sorry, H acting on where?
On the free vacuum.
No, this we don't know what this guy does on this.
It has overlap with the we don't know exactly, but we don't know what it gives, but it has some determinant which is like E0.
Well, in fact, the argument actually goes. The argument of how this guy is dropped, we could have done it before dividing by this. So we could have put this guy here, right? Imagine that we had kept this guy here. And then we ask, we don't know what this guy is, so we leave it there. So this operator will go here. This factor will go here. We will not have an E0 here, okay? And then what we do is to say, well, in fact, that's really what I'm doing. I'm factoring this out. So let's see, what did I do? Well, let me write it the other way around. So where we did it over there. Okay, let's actually do it over here. Yeah, it's important to see how it happens, right? So what we have is that e to the minus I t plus t0 E0 on this guy is equal to e to the minus I t plus t0 h 0 minus integral sum of e to the minus I t plus t0 en and the rest. Okay? So the relevant part, of course, is going to be something that looks like e to the minus epsilon e0. The relevant part here would look like e to the minus epsilon en. Okay? Do you agree? So when you take times something that we're going to take very large, so we could give it a name, but let's not bother. Let's just put infinity. So granted, this thing goes to 0, right? But all these guys go exponentially faster than that one, okay? So we're using a trick where everything goes to 0, but these terms go exponentially faster than the leading order term. Therefore, we can conclude that we can drop this and just keep this guy equal to this. And that's the formula that we landed on here, okay? Is that clear?
Right, so it makes sense that you have to assume the vacuum to do this. You also have to assume something about the relative spacing between the first excited state and the 0, or do you just assume that the time is big enough?
Yeah, we're taking this to infinity, so I think this is pretty safe. Okay. Okay, very good. So now comes the next little manipulation that is a little bit funny, which is to call this t0 minus minus t, minus not this t, the other t, before we actually write it as an evolution operator, okay? So now if we want to write it as an evolution operator, what do we have to do? Well, we just have to multiply by the corresponding h0 and then write it as an evolution operator. And that gives us well, the point is that the vacuum, right? So in this case, it's actually easy because this is a vacuum. So we can freely multiply by e to the I tau or capital T h0 acting on the vacuum. This is actually the vacuum, right? So we can substitute this and put this in here. And when we put this together with this, we produce nothing but the evolution operator from T0 to minus T, or to minus capital T, acting on the vacuum, okay? And we get the same thing that we had here. Okay, so that's our formula for the vacuum. Yes?
Don't we get our vacuum energy when we do in the free theory?
The vacuum energy of the vacuum? You mean our all infinite friend? I thought we were, we decided to forget about that. No. No, I mean, here we're assuming we don't have gravity. So we are completely renormalizing, or even if we had gravity, so we would just introduce something in the Lagrangian to eat it up, okay? So we define the energy of the free theory to be 0, of the free vacuum to be 0. But that's a good question, yes. Well, by the way, that's an important thing. So every time that we're doing something here, you should go back after the lecture and think, well, what is the thing that you think is the weakest link of what I'm saying? And try to think deeper, in a deeper way about that, okay? So I'm not going to do it, but a similar trick we can apply it to this object in order to get it. But it's a slightly different trick because I'm going to put the T0 value with a minus sign. Okay? So that's why it's not just the dagger of that. In the limit, it doesn't matter because this is an infinite limit. But we will just get this quantity. And don't worry too much that we're almost done. Okay? We have all the pieces now, all the pieces of our puzzle. We have the operator, we have the vacuum, actually both of them. So we have this guy. All that is left is to put it together. Okay, so let's do it. Let's put together, let's assume that x0, after all, there is a time ordering operator there. So let's take the time ordering operator and expand it. And let's consider one of the cases first. And in fact, let's assume that our reference time, t0, now this t, the 0 means something different from these zeros. Yeah, another clash of notation. That's very unfortunate. This 0 means that this is a reference time, and this 0 is the 0th component of x and y. Okay? So if this is the case, then our Green's function is nothing but this with phi okay? And that is the object we want to compute. Okay? Well, in fact, before we do that, let me also do something here. Given that we have this guy and that guy, it seems natural to compute this quantity. What did I tell you this was? 1, because it was normalized. Okay? But then if we put the two quantities together, we get the limit when this goes to this funny location at infinity of this operator acting or composed together with that one, okay, from t0 to minus t, divided by e to the, when I combine this with that, you see the sneaky choice of sign actually works out. The t0 drops out, and I get minus 2 t e0. And I get the norm. Sorry? Oh, yes. Thank you. So this has to be equal to 1. So if we ever happen to see this object in the calculation we're going to do, we can freely replace it by the numerator, okay? Because this is equal to 1. And not only that, by the composition or by the group rule, this means that we can put these two guys together and drop the t0, and it's the evolution from minus capital T to t. Under the assumption that we're taking the limit, this thing is then equal to e to the minus 2i tau, or capital T, e, the norm of the overlap, okay? So I'm going to put quotation marks here because this is only true when we're taking the limit, okay? Now let's do this, yes?
Clearly, the norm of your baking doesn't depend on the reference time, right? But does your vacuum depend on your reference time?
What depends on the reference?
No, nothing. I mean, the norm doesn't depend, right?
Yes.
But does the vacuum itself depend on the reference time?
No, this is a state. Time here is a parameter. This is a state in the Hilbert space. There is no, this object doesn't evolve in time, it's not a section, no, it's a state in a Hilbert space. Okay? That's the way I prefer to think about this. There is a state in the Hilbert space that describes, this state describes the reality of something in the whole space-time. Okay? Okay. Let's put the pieces together. Yes?
So, I mean, we are also kind of, at the beginning, we were talking about being in Heisenberg picture, right? So,
yeah, after all these days, I've come to actually dislike the picture thing. There is no picture anything. I mean, we should really think about states in a Hilbert space, and there are operators acting on them. Then people say, well, that's the Heisenberg representation, where the states don't depend on time. Then the Schrodinger one is where you take these guys and you act with the evolution operator. But it seems to me that it's more fundamental, or it looks nicer in this context to think about just states that describe nature, right? A state of nature. And then there are operators. And you do things with the operators. And the operators depend on, it's more relativistic to think about time also as part of a space-time. And then there are operators located here, here, here in different places. Yes?
It's still not clear to me that if I take the limit when the spanning t goes to infinity, that T0 doesn't appear after I take the limit. Right?
Well, it does appear. What do you mean?
But so if it does appear, then for a different reference time that I can take, then I have a different rate. Right?
No, this quantity.
Right. I mean, after I take the limit.
This quantity is independent.
Of T0.
Yes, of T0. This quantity.
It's not clear to me why.
Well, because any dependence, just change T0, take the derivative with respect to T0. Change T0 by infinitesimal constant, by infinitesimal value. Or just change it by anything that you want. Then whatever you're doing here must be of the order, the change will be of the order of the change in T0 divided by this guy, right? I mean, the change, whatever change you're making, is going to be of the order of the change that you make to T0 divided by this. And that object is going to 0, right? Okay, so finally, let's put the pieces together. The moment we all have been waiting for. Of course, there is a limit. Okay? Now we have to put all the pieces together. The vacuum, which is evolving from T0, which is a time evolution operator from T0 to this time. Now, phi of x, we're going to use our formula over there, okay, with a check mark, which tells us that is u dagger of t, or x0, T0, phi I of x, u of x0, T0. Now we do the same thing for phi y, u dagger y0, T0, phi I of y, u y0, T0. Good luck trying to write this down on your notebooks. You have a big blackboard. Now we're only missing the other vacuum, right? The other vacuum is u of what? Thank you, T0 to minus calligraphic T of the vacuum. And all that divided by what? Well, by this guy times that guy. But isn't that nice? That's what we computed. So this is starting to look very pretty. I mean, compared to what it was. actually very nice. Very good. Okay. Well, can we simplify this a little bit? Yes, look at the numerator. These two guys, we can immediately combine them, right? Because this thing is u t0 y0. Now, by the composition rule, it mixes with this guy. It composes with this guy to give us a very nice operator that only depends on y0 and x0. Same thing for this guy. So we get the limit tau goes to infinity of 1 minus I epsilon of u from this to x0, or from x0 to this time capital tau, of phi I of x, u from x0 to y0. It's funny, this formula is kind of telling us a story of something that is happening, right? But I'm reading it backwards. It's really annoying that I have to write it like this. It'd be nice if I were writing it the other way. So the formula is telling us that our Green's function is obtained by taking the free vacuum, or the state that represents that, but in the full interacting theory, right, which belongs to the same Hilbert space. And then somehow the story is that you evolve it to the time y0, then it's interacted with this guy, which then the whole state is then evolved to this other time, and then you interact with this operator, then you evolve it to a later time, and you compute the overlap with this state again, okay? Well, that object is basically what we wanted to get, except that we can even make it a little prettier, okay? So in the lecture, we have been making things prettier by using what has been our main source of making things prettier. When the what? That has been one, but also there is another one. For instance, how do we write Dyson's formula in a nice way? This was kind of a mess. We use the time ordering to write it in a beautiful form. Right? That's what we're going to do now. So we're going to write our, in fact, now, if we use the time ordering, we can put everything together and say that this is the limit when tau goes to infinity, 1 minus I epsilon of. Now, here comes what we're going to do. We're going to put the time ordering. And under the time ordering, we said that everything can be treated as if they commuted, right? Because the time ordering will take care of that. So when we put it in, you see that if we can treat these things as if they were commuting objects, wouldn't it be nice to move this guy and put it next to this one? And then compose it, and then move it pass through this and put it next to this one, and then compose it again. Well, then, if it's nice, why not do it? So we're going to be left with phi here at x and y, and now u of the whole thing and this is our formula. That is truly spectacular. It's a beautiful formula. And not only that, yes? Yes, okay. That's why you were not in awe and amused, because it was I spoiled the moment. It was. Now we can all say, wow, This is really amusing. Spectacular formula, especially because we know what this thing is. So now this object is, so we can put the time ordering here too. Well, this guy has a time ordering. So in fact, now I can even remove this guy and replace it by its definition. Just one second. So e to the minus I integral from minus t to t of dt prime hi of t. And here too, okay, yes.
So, I mean, so I guess time ordering, I'm a little not absolutely sure about the interpretation of the time ordering since our time now is so complex. So I guess it's
think about it as a path ordering now. That's why previously it wasn't an accident when I said that you could even complexify the time when we were discussing. Well, it was an accident really, but it fit perfectly with. So this is our formula, okay? Not only is a nice formula, it's also very, very, very interesting that if we take, say, remember we had our interacting, or our, sorry, we have, let's see how much time we have. Okay. So what is this in a, well, we did all this without really assuming what hi was, all right? So what is hi? Let's actually think about it. So in our example, the one we didn't write it here even. This formula is completely general. But if we were considering this guy would be nothing but lambda over 4 factorial integral d3x phi to the 4th I x. Okay? Yes, it started its life as a Hamiltonian. So now when we put this in here, you see that the t is very nice. The t combines with the x to give us something that is a Lorentz invariant measure. So in fact, the object that appears all over the place now is an integral from minus t to t d4. Then we can think about, if we really take this seriously and we take infinity, okay, except this slightly complex contour, we get something that looks like this with lambda 4, okay? Or, if you wish, this is nothing but minus, in general, the integral d4x of the interacting part of the Lagrangian evaluated on phi I. Yes?
Why are you writing phi I and not something else?
Well, remember how this guy was defined? Do you remember? Look in your notes.
That's h naught, h minus h3.
Yes, but then acted on with this e to the I h0, which was precisely the definition to get an h. That was a discussion we had with Tibra. He suggested that this object should be called h int of I, but I refused to do it. And the reason is that, well, obviously it takes too long to write it. But this is the definition we mean, where this guy would then be h int. Okay? Very good. So let's stop here, and then if you have any other questions, we can discuss. We can let's move the discussion session to right now instead of having it as part of the lecture. It's just that I have to go to somewhere in 10 minutes. So.